Hi, my name is Frankie. I'm an assistant professor at the Colorado School of Mines, specializing in space robotics. You're tuning into the first lecture of my space robotics course, SPRS509, where in this lecture, I will introduce space robots. In this lecture, I hope that you'll be able to understand the definition, classifications, and unique design considerations of space robots. I also hope you'll be able to understand how space robots have evolved over time and their role in space exploration. Let's define a space robot by its constitutive parts: space and robot. Space is the environment beyond Earth's Kármán line, which is about 100 kilometers above sea level. This is where orbital dynamics, microgravity, and harsh conditions, such as vacuum, radiation, and temperature extremes, dictate spacecraft and mission design. You can see that distinction of the Kármán line in this background photo. Robots are a functional machine composed of mechanical, electrical, and software components. Mechanical components define the structure and actuation. It's the physical framework and moving parts that enable mobility, manipulation, and interaction with the environment. Electrical components define the power and sensing capabilities of the robot. This includes the circuitry and power systems that enable sensing, communication, and actuation. It's like the lifeblood of a space robot. Software components constitute control and intelligence of the space robot. It's the algorithms and decision-making logic that process data, control movements, and enable autonomy. It's like the brain and the different electrical signals that we send throughout our body. Past defining what a space robot is, we can classify space robots into different classifications, like the kind of environment that they were designed for. Three major classes include orbital space robots, planetary space robots, and aerial space robots. Orbital space robots include robots that reside in microgravity environments, which includes orbits around our home planet Earth, but also orbits around other solar system bodies like Mars. These orbital space robots are called orbiters, or could also be called satellites. Planetary robots include robots that reside on a planetary surface, which includes asteroid bodies, comets, moons, and planets like Venus, Mars, and then moons like Titan. These are some examples of what it looks like on these planetary surfaces. Planetary surface robots can take the form of landers or hoppers or probes or rovers, most famously. Think of any robot in space that interacts with an extraplanetary terrain. Aerial space robots include robots that leverage a planetary atmosphere. Some planetary bodies outside of Earth have an atmosphere, such as Venus, Mars, and Titan. Aerial space robots may take the form of a balloon, rotorcraft, or lander while still in flight. The key characteristics of these aerial robots is their critical interaction with some kind of atmosphere. In the next few slides, I'll give examples of some famous or notable space robots within these categories. A famous satellite under the category of orbiting space robots is the Hubble Space Telescope, which can be seen here. Hubble Space Telescope has the function to be a sharp pair of mechanical eyes in our sky. Roboticists on Earth like to study robotic arms, so I thought I'd also call out a famous robot manipulator, Canadarm, that's orbiting in space. And you can see that Canadarm over here. Canadarm is provided by the Canadian Space Agency as a part of the International Space Station Collaboration, which is the robot or the space station that Canadarm is connected to. Canadarm's job is to dock with spacecraft and potentially move those spacecraft around for assembly, as well as move astronauts around the space station for exterior maintenance. A recent orbiting mission that I found exciting that mixes satellites with manipulators is the OSAM-1 mission, which can be seen here. Its capabilities are in its name: to service, assemble, and manufacture in space. OSAM-1 can rendezvous with other satellites and service these satellites, like the picture is showing here. Independently, OSAM-1 can also assemble parts in space, like lens components into a telescope array and manufacture an orbit, which can get around the geometric constraints of fitting structures in nose cones of rockets. Of a few planetary surface vehicles, Some notable examples are the Perseverance rover on Mars, and then the Tonga lander and the U-2 rover on the bottom here. Here's a picture of Perseverance taking a selfie of itself. And then here in the corner is a picture of the Tonga lander looking at the U-2 rover driving away on the far side of the moon. A very recent planetary surface robot that successfully landed on the surface of the moon is Firefly's Blue Ghost lander. An artist rendering is shown here. On board this lander is a Honeybee Robotics drill, the Lunar Instrumentation for Subsurface Thermal Exploration with Rapidity, or LISTER drill, which sent sparks flying during the experiment in their downlinked video, of which here's a snapshot. You will have to Google it, it's awesome. This robot will help us understand the heat flow from the lunar interior to the lunar surface. We don't have too many examples of aerial vehicles, but that's okay because I'm rather inclusive when it comes to my space robot friends. Some aerial robots that come to mind include two Venus probes, Vega 1 and 2, which were passively drifting balloons that floated along Venus's atmosphere with the winds. In the corner here is the Huygens probe's concept of operations, which shows the entry, descent, and landing robotic solution that was totally autonomous in jettisoning a heat shield and deploying 3 parachutes to eventually land the Huygens probe on the surface of Titan. A very clearly identifiable aerial space robot is Ingenuity, our Mars helicopter demonstration from 2021 that proved that we could actively control flight on Mars. Given that the atmosphere on this planet is 1% of Earth's, generating enough thrust to propel itself is quite an achievement. You may be wondering, why is designing for space hard? There are unique design considerations when designing for space environments. We defined outer space earlier by its distinction from Earth, its distance from us. This also includes how the gravity in space is different than on the surface of the Earth. This also includes how the atmosphere is going to change by density and pressure, where a lot of space is vacuum. We also need to consider radiation levels in space that vary. These are all design factors that imply different considerations in designing spacecraft. Let's talk a little bit more deeply about distance. The two ways that distance impacts the way that we design and operate spacecraft comes in the form of communication delays and anticipated power generation. The image here shows the distance in light as measured in time between Earth and the various celestial bodies in our solar system. The signals that we send from these planetary bodies move very quickly at the speed of light, but that still takes time, which manifests as a communication delay between when a signal is sent from a spacecraft to when that signal is received by a ground station here on Earth. These communication delays are how long we should expect a lag in a robot receiving a command from Earth, or how long we should expect to wait for data to be downloaded or downlinked from space. The other way that distance impacts the engineering of a space robot is the energy you should expect your spacecraft to generate. This plot over here shows the percentage of solar intensity each planet in our solar system receives relative to Earth as a function of distance. So you can see our planets, Mercury to Pluto, and you can see a trend that's decreasing as the distance increases. The y-axis is the percent of solar intensity on a log scale. So you'll notice that the tick marks increment in magnitudes of 10 in units of percent. The x-axis is the relative distance of each planet from the Sun, also in log scale in units of AU or astronomical units. As your space robot moves closer to the Sun, your robot will receive more power with distance squared, and conversely, as the robot moves farther away from the Sun, the robot will receive less power with distance squared. The squared relationship looks linear in log-log scale, but on linear scale, it would look like a sharp drop-off. But isn't that a cool, beautiful mathematical reminder of log scales and relationships? Let's now talk about gravity. The different celestial bodies in our solar system have different masses, and that dictates the gravity on a planetary surface. Smaller bodies have less gravity, and as you know, gravity dictates the physics of projectile motion, which dictates a lot of the interactions we personally observe on Earth. An example of how this impacts a space robot is a story of Philae. Here is a composite image, a picture of European Space Agency's comet hopper Philae and its journey as seen from the orbiting Rosetta spacecraft. Philae was caught in action as it traveled above the surface of comet 67P, or also known as Churyumov-Gerasimenko, where it bounced 4 times across the surface like a skipping stone before resting in its final touchdown position. Space's vacuum environment differs from Earth's atmosphere in that heat is transferred differently. Here on Earth, we can rely on convection, or the transfer of heat through fluids. In vacuum, robots cannot rely on convection. Instead, spacecraft can only rely on conduction and radiation. You can see this image, a flow diagram of heat channeling through a spacecraft, in this case, a rocket. There are many sources of heat that radiate to the spacecraft from the sun and from Earth, also conducted through heat from internal spacecraft components that can only be radiated away in black-body space, indicated by that red arrow. Okay, while I was talking about radiation just now in the context of heat transfer, we need to talk about radiation in a different way on this slide, as radiation pertains to high-energy particles in a different definition, but still in space. On Earth, our magnetosphere protects us from a lot of the harmful radiation that's generated from the sun. But once a robot travels into space outside the comfort of a magnetosphere, this space robot is subject to a broadband radiation that includes galactic cosmic rays, solar energetic particles, UV, and all the other high-energy particles. Just like how we have to protect our skin from UV, these rays can degrade a space robot's surface coatings, which is like the skin of a space robot. These particles can also penetrate past a space robot's shell and interfere with electrical signals by flipping bits, which can produce nonsensical signals to a space robot's computer. Even though space is a harsh environment, which makes designing space robots hard, we as a human race have accomplished a lot outside of our rock floating through the vastness of space. Along the classes of space robots, we have matured technologies and evolved our space robots to become more and more capable. We'll cover this more in depth in a future lecture, but some notable firsts include the first orbital spacecraft, Sputnik, around Earth in 1957. In the planetary class, the first lander on another body of the moon is Luna 2, and that happened in 1959. The first mobile robot on another planet was on the moon, and its name was Lunokhod 1, which happened in 1970. The first passive aerial vehicle on another planet, Venus, was Vega 1 in 1985, and the first aerial vehicle on another planet, Mars, was Ingenuity in 2021. If I were to speculate to the next step in our accomplishments, I'd speculate we're bound to operate a space robot on an ocean world or icy moon next. The trend of capability over time generally follows the environment's difficulty to access, where orbits are the closest and easiest, and icy moons, which are around Jupiter and Saturn, are farthest and the most difficult to access. Let's get more in-depth about specific capabilities or roles associated with our space robot evolution. For orbiting space robots, the hierarchy of capabilities necessitate that we need to be able to launch robots and insert robots in orbit before proceeding. Space robots then need awareness and the capability to observe. After that, robots can move on to navigating and moving through an orbital environment. Finally, a robot can manipulate the environment or objects within the environment. We talked about OSAM-1 previously, but I think by following the concepts of operations of OSAM-1's mission, we can see this sequence of capabilities, of it first making it into orbit, observing a satellite as a target, rendezvousing with that satellite, and then manipulating that satellite. For planetary vehicles, a similar evolution in capabilities can be seen. A space robot's role progressed from just landing, which is a lander or probe, to moving around a planetary surface to do some in situ science. Rovers then get more advanced and start manipulating the environment by sampling rocks. These capabilities are well demonstrated in Perseverance. A capability yet to be seen in space is a robot developing a planetary surface, colloquially known as terraforming. There are many concepts on Earth that I would love to see in space, such as Razor, but none have flown yet. Aerial space robots have evolved in their role from just being an entry, descent, and landing solution to becoming a standalone robot to scout safe terrain for planetary rovers. These capabilities are demonstrated well through Ingenuity. Current aerial vehicles are limited in power, which limits range of the vehicle and prevents more comprehensive mapping coverage of a planetary surface. These are concepts that have to overcome these design obstacles. Since we've never sent a space robot to the surface of an ocean world or icy moon, these capabilities that I have listed over here are entirely based on proposed mission concepts and not on proven capabilities. This here is an artist's depiction of the NASA EELS mission concept, which shows a snake-like or eel-like robot propped against opposing faces of an icy crevasse on the surface of Europa, which is a moon of Jupiter. On an icy moon like this, with an ocean world underneath the ice surface shell, a robot would likely have to drill or burrow beneath the ice. Once past the icy shell, the robot would have to slither or swim through the ocean. To increase the effectiveness of its exploration, this robot would need to navigate the subsurface environment somehow and perhaps investigate samples or transport samples. This slide collates all the space robot roles we saw in previous slides, where the yellow verbs are the space-proven capabilities and the orange verbs are the unproven capabilities. You can see the evolution of capabilities and roles that robots in space have taken on as we explore more of space. While autonomy is not explicitly a role that a robot takes on, autonomy indicates at the amount of a role the robot takes on. The spectrum of autonomy ranges from teleoperation, which is operation from a human and is entirely not autonomous, to fully autonomous, which is when a robot makes all the decisions in its operations. Our historical missions relied heavily on teleoperation, but we have evolved in our relationship with robot intelligence in allowing robots to take on more and more responsibility in performing its own actions through automatic operation and making its own decisions through semi-autonomous operation. We may see fully autonomous space robots one day. I hope by the end of this lecture, you can now define a space robot, classify a space robot, and define unique design considerations associated with that space robot. I also hope that you've come to understand the evolution of space robots and the roles that space robots have taken on in the history of exploration.